Hi, everyone. We're here to discuss the travel demand modeling process as part of the Fundamentals of Transportation Engineering class. And so this is chapter 4 of your textbook, Fricker and Whitford. So I'm going to go ahead and share my screen here. This is your class portal, and then this is the week 4 that we're dealing with. And then for week 4, I already posted videos for chapter 6 and chapter 5. So this is chapter 4, the slides for which are posted right now. And then I put in some reading assignment, the sections of the textbook that you need to read. And as you know, so these are the sections you need to read. And then as you know, your textbook is right here if you want to look at the PDF version of the textbook, Fricker and Whitford. So, so as part of the chapter 4, we're going to get started here. So your learning objectives for chapter 4 are, you want to list the steps of the planning process. And then we'll get into, once we've listed the steps of the planning process, we'll get into the travel demand modeling process, which is sort of a 4-step process typically. There is this whole other way of modeling travel demand, which is called the activity-based modeling. We're not going to get into all of that in this class. If you're interested in activity-based modeling, you'll have to take CE 523, which is our travel demand modeling class, where we go into these 4-step demand modeling process, as well as the activity-based travel demand modeling in much more in-depth. So these are the 4 steps: the number of trips generated to and from an area, number of trips going to a particular destination, and then particular mode choices that people are making, and then look at the equilibrium concept to estimate the traffic flow division between different routes. And then we'll talk a little bit about the strengths and weaknesses of the planning process. So what does transportation planning process actually entail? The transportation planning process entails analysis of current travel patterns, and then using those current travel patterns, forecasting the future patterns. So that's your chapter 4. And then once you have an idea about what your demand looks like, you will translate that demand into what will satisfy those demand in terms of infrastructure options. So, and then we evaluate those options, and that's what we learned to do in chapter 5. The result of the process is a set of improvements to be considered by decision makers for implementation in the near or midterm future. So that's your planning process. But in this chapter, we're going to deal much more with chapter 4, where we're looking for how many trips are going to be made, what modes they're going to be using, and what type of routes they might be taking, and so forth. So this whole process of what we're going to learn about in chapter 4, it's called travel demand forecasting. And one funny thing about forecasts is that all forecasts are wrong. Some forecasts are more wrong than the others. So this is sort of getting at the accuracy of the forecast, right? How accurate your forecast is going to be about the future. And then the second one is all forecasts are wrong. Some forecasts are useful. And what makes a forecast useful is that if it's a little bit of a precise forecast, right? So for example, if I want to tell them that, hey, if we open up a bus service from San Luis Obispo to Santa Barbara, anywhere between 100 to 90,000 people are going to use it, my forecast is probably fairly accurate, right? If I say between 100 and 90,000 people are going to use it over a week, right? My forecast is probably going to be accurate because the number of riders on that bus service are going to be within that number. But that forecast, is that actually useful? It's not a useful forecast because I have such a big range. So when I say some forecasts are useful forecasts have a characteristic of being precise in nature. They're not very wide-ranging. They are narrow range so that you can make decisions based on those forecasts. Like, for example, how much bus fleet am I going to need? I cannot decide that based on an accurate forecast that ranges between 100 people per week versus 90,000 people per week. That's a useless forecast, even though technically it's likely to be accurate. So useful forecasts have to be precise, and accuracy and precision, and those are distinct concepts. That's also another thing I'm trying to convey here. When you are correct, that's an accuracy issue. how correct you are, and then how precise you are. Are you able to forecast in a narrowish range so that decisions can be made based on that? Those are what we call the precise forecast, and those tends to be more useful. And forecast is essentially a tool to identify needs and evaluate options. So identifying needs is the travel demand estimation. That's what we're learning here. And then evaluation of options using time value of money and the engineering economics concept. That's what we learn in chapter 5. So these are the basic 4 steps of the travel demand modeling process. Trip generation. Here we make an estimate of how many trips are leaving or entering a zone I or zone J. So when we are doing travel demand forecasting process for a region, for a city, for a community, we divide the region into what we call traffic analysis zone, or TAZ. So when I say zone, the term that I use is TAZ, and those are your traffic analysis zones. And we divide the area into those, and then those sometimes would be, coinciding with the census boundaries. And that is very helpful because then we can use the census data directly, or there might be some other zoning patterns we might use if data is available for those, but typically those will be your census zones. And then based on the population patterns, how many jobs are in a particular zone, we can figure out how many trips total will be coming to that zone and going out of that zone. So that's your trip generation step. So that's just aggregate number of trips coming in or going out of a zone. Now, when we go to trip distribution, we're trying to estimate now, let's say there are 1,000 trips coming to a certain zone, where those trips are coming from. Which zones are they coming from? So now we are basically in trip distribution step, we are coming up what we call the OD pairs. So an OD stands for origin destination pairs, right? That's your OD pairs look like, origin destination. Now I'm trying to relate not just the aggregate number of trips as I was doing in trip generation. Now I'm trying to figure out where those trips are coming from. So now I'm distributing them between the zones. So that's what's called trip distribution. Then once I've done the distribution, typically this is a sequential steps, mode choice. How many trips from zone I to zone J, and those are sort of generic terms, I and J, that I'm using to specify the traffic analysis zones, are using a particular mode. Are they going to be drive alone mode? Are they going to be carpool mode? Are they going to be using bus, a train, a pedestrian mode, a bicyclist mode, what it is? So I'm basically now dividing the trips into different modes, and that's your mode choice. And then once I've figured out the mode choice, and let's say if I know how many people are actually going to be taking their own car, personal automobile, then I want to potentially divide those trips into what I call the trip assignment. And a lot of places, what you will see is that trip assignment step is also known as route choice. What route are you going to be taking? So here we try to divide the total number of trips we have going from one location to the next other location. We try to see if there are multiple routes, how the trips are going to divide themselves. These steps, basically, what are these steps? These steps are aggregation of the decisions that we make as individual for our own trips, right? So think about, and you will see it, right? When we talk about these 4 different steps and details of these steps and how to solve problems using these steps, I'll ask you to think about connecting that to your choices of, where we live is related to where we are going to shop for groceries, for example. We are not going to go to a further location for grocery shopping. We're going to try to keep it close, as close as possible in general. And then, if there are routes we are choosing, then we try to minimize our travel time. And that's something that we do. So these steps are basically what they're trying to do is they're trying to aggregate the individual choices people make as they go about their travel patterns And these decisions are modeled using travel diary surveys. A lot of these could be obtained from the census surveys as well. So you'll see the different types of data that are being used for these travel demand modeling steps. So let me go ahead and clear. So let's talk about the first steps. The first step is the trip generation step. How many trips are entering or leaving a zone? Now, I say here the zone I or zone J, but in a lot of cases, this is not something we always do. Sometimes the trip generation is also based on the nature and intensity of the land use. For example, if you have a new restaurant coming up and you're trying to figure out how many trips is this restaurant going to generate, how many car trips, we can use what we call what we have a resource called ITE trip generation report, and we can use that ITE trip generation report to use the data in that report to estimate how many trips are going to be generated. Now, this is here, the restaurant is considered its own zone, so it's not necessarily we're talking about, you know, a zone within a city or anything. We're just trying to figure out how many trips are going to be generated by this land use. And that can be important to us to figure out, you know, how do we mitigate these number of trips? How do we make sure that maybe there are fewer car trips that get made, or how do we accommodate those trips that are going to be made? So sometimes it's not necessarily about doing the trip generation for a zone I or a zone J of the city. Sometimes it could be just for an individual land use. So planners a lot of times have to do that. And for that, we use the ITE trip generation report. ITE generation report is basically filled up charts like this. I hope you can all see that here. But I'm going to try to spotlight things. So this is basically trying to figure out what type of trips, what number of trips are going to be generated by a manufacturing area, manufacturing plant. Average vehicle trip ends. When I say trip ends, that's basically the number of trips that are going to be generated versus 1,000 square feet of gross floor area. So this, and on the x-axis, you have the gross floor area of the factory, of a manufacturing facility. And then T is the number of trip ends. And then you could see there is a chart. If you, basically it says number of studies 62. Basically what that means is that if you look at these X's and if you count them all, there are actually total 62 studies that were conducted to create this chart. So they looked at 62 different manufacturing facilities and they counted how many trips are coming in and going out at different times of day. For example, this is for a weekday. So this is for a weekday. So this is the total number of trips per day. And then this chart is basically a regression equation that is estimated using how many trips at those 62 locations were generated. So for example, they observed a facility that had approximately 1,000 square feet of area, and it was generating about, you know, for this point, for example, if I'm trying to figure this out. So for this point here, it had a 1,000 square feet of area, and it was generating about 1,000 trips. If I'm looking at this point, for example, it had about, you know, if I draw a line from this, I could draw a line from here to here. So that's had about, if I'm reading this correctly, about 1,200 square feet of gross floor area, and it was generating about maybe 5,400 trips were being generated, right? So, and then once they had all these 62 studies collected, they fit a curve using a linear regression equation. And this is the equation they came up with. That's right here. Okay. The R square is pretty good, 0.87. That means it's a good fit. We typically want to rely on these fitted equation when my R square is higher than 0.75. If it's lower than that, then I get a little bit iffy. If it's lower, like 0.1, 0.2, then I don't want to rely on the fitted equation because I don't trust the equation. In that scenario, sometimes we rely on the average rate of trips. So the way you use these charts is that if you have a new manufacturing plant coming up in an area and you're trying to figure out how many vehicle trips it's going to generate, it's going to be, let's say if there was a 2,000 square feet plant coming up, okay, and you want to find out how many trips are going to be generated. So your question here would be number of trips generated by a manufacturing plant of 2,000 square feet of GFA, which is the gross floor area, right? So how do you solve a problem like this? You solve a problem like this by applying this equation right here. So the number of trips, total number of trips, T, will be equal to 3.881 times X times 2,000 plus 20.702. Okay, here is a problem though. I have made a big mistake here. This 2,000 is actually not correct. Why is this not correct? Because my x-axis is in thousands of square feet area, and I'm giving 2,000 square feet of area. So that means this 2,000 shouldn't actually be 2,000. It should be just 2, because it's 2,000 square feet of gross floor area, because the unit here is 1,000. So whenever you're trying to, and then you can, it's just simple arithmetic. You can solve this equation and get the number of trips, and I'll let you guys do that. But the point I want to make here is that when I'm reading these equations, when I'm trying to read this, this chart here, I have to be very careful about the unit on the x-axis, unit on the y-axis. This is total number of trips on a weekday. There are different charts for just the peak hour, afternoon peak hour trips, like between 1 to 2 p.m. or 3 to 4 p.m., for example. There will be a midday number of trips during midday. There might be a morning peak hour trips, like from 7 a.m. to 8 a.m. So you have to be very careful about what you're trying to estimate and what you're looking at in the chart. I have a separate video courtesy of Dr. Kimberly Mastico, who used to be a lecturer here at Cal Poly. I posted a separate video from her that talks about how to read this chart, and she has a lot of valuable information that you could use then. Now, one more question is that what if I wanted to solve if this R square was fairly low, if this R square is 0.87, which is pretty good, but let's say in some of the charts, the R square could be as low as 0.01 or 0.12, things like that, way lower than 0.75 threshold, where we start to deem these models to be more reliable. So this model is fairly reliable. So in this case, I would probably rely on the fitted curve equation, right? That's pretty good. But in some cases, I might have to rely the average rate if my R square value is lower than 0.75. Now, if it's right at 0.73, 0.74, I might still go with fitted curve equation. So there's no absolutely right answer here. But if my values fall below, like 0.5, 0.4, something like that, then I get into a territory where I have to rely on the average rate method. And the average rate method is pretty simple. The trip generation per 1,000 square feet of area is 3.82. If this is the average rate for a 2,000 square feet factory, I will have the average is 3.82 times 2. And you can start to see that, these numbers could be very different from each other. And again, I'll let you do the arithmetic here, but suffice it is to say that the numbers that come out of the fitted curve equation or the average rate could be pretty significantly different in some cases, and maybe not as different in some other cases. So you have to be careful about what models you apply. So in this case, because the R square is very high, I will probably stick with this method. So this will be sort of the right method for me, and not this one. So I'll use this method right here because the R square value is fairly high. But in some cases where it's not, then I can rely on the average rate method as well. And you should be able to apply it as well. Now, you only want to apply these when your question is sort of in that range. So for example, all of these ranges were, so So there is no data point for more than 2,000 square feet. You could see like maybe no more than 2,200 square feet. If I look at the point that's way to the right of this, so I'm looking at maybe 2,200, something like that. There's no data point beyond that. So if I'm trying to figure out what would be the number of trips generated by a 3,000 square feet of gross floor area location, 3,000 square feet of gross floor area location, I probably would not want to rely on these studies because they are sort of out of range. And then I might have to maybe conduct another study where I look at the larger plants, or maybe look at something else, some other resource or something. But I want to stick with the range that I provided. For the purposes of this class, all the problems you're going to solve are going to be in that same range. The other thing I want to point out is that look at that equation carefully. Sometimes there is logs in these equations as well. Sometimes the fitted curve equation might be a log equation. So whatever is in the equation, just make sure that you apply it fairly carefully. And I have another video where Dr. Mastico explains reading these charts in a little bit more in depth. And I have provided that video on your Canvas page. So make sure that you look at it. So this was sort of the number of trips being estimated using based on the land use that you're having, like manufacturing. You could do this for restaurant. You could do this for gas station. I believe I posted a problem like this on gas station online. So you should look at that video as well. But now that you've learned about the land use based trip generation, let's think about how we're doing site-by-site analysis may not be very efficient when you're trying to do the travel demand modeling for a region. We only do it when we are interested in the impact of an individual facility. That's when we do the site-by-site analysis. In other cases, when you're trying to basically model the travel demand for a region, then we do the TAZ-based analysis, traffic analysis, zone-based analysis. Instead of detailed locations for each trip may be assigned to a TAZ, maybe a city block or a 1 square mile region, or boundaries are set to coincide with census blocks. And that sort of is the most common thing that we do. And then based on the characteristics of that census block, we can rely on what we call the regression analysis. Regression analysis is nothing but an equation where analysis of numerical data consisting of value of a dependent variable, and then analysis of numerical data consisting of value of. So what we do is, so number of trips are our dependent variable, the response variable. In this case, in our case, the response variable is number of trips. And then independent variables in our case would be population, number of jobs that are housed in a particular location, schools in a location, dwelling units could be another one. Dwelling units basically is a fancy word for houses, how many houses or apartments in an area. So those will be our independent variables. So sometimes we can forecast the number of trips using these characteristics of a traffic analysis zone. And again, because the boundaries are typically coinciding with the census block groups, these numbers can be obtained, of these independent variables can be obtained for a zone from your census data. And again, you won't have to, for the purposes of this class, you won't have to get the data from the census. I will just I will just provide you with these characteristics, and you'll have to estimate the number of trips. So this is what a regression model actually looks like. You can see that. Let me highlight this here. T is the number of trips. It'll be equal to A naught, a constant, times A1, X1. X1 could be population. X2 could be number of jobs, for example. And there could be n variables like this. X1, X2, X3 are household characteristics for home-based trip generation. And if you're talking about non-home-based trip generation, those will be more like employment characteristics, right? So sometimes we do this modeling for a zone where there are a lot of homes, then you'll basically have household characteristics as your X variables, as your independent variables. But if you're talking about a CBG, which is the Central Business District, CBD, I'm sorry. So if you're talking about a CBD, which is Central Business District, So this is your downtown area. A lot of time, your trip generation will be based on employment characteristics of a location, like number of jobs, and then for home-based trips for a neighborhood, the trips will be based on. So this will be based on, like, how many houses are there, what is the income of those households, how many cars do they own, and things like that. Okay, let's see. So this is a very simple example that I want to work with you here real quick. I'll let you again do the the arithmetic of it on your own, but let's think about this. You're given these two regression models right here. So I'm just going to highlight these, TI and TJ. And this is a model for AM peak hour. This is for the morning peak hour. Planners have estimated the following models. TI is 1.5 HI, where HI are a number of households in a particular zone, and TJ is basically number of trips attracted to a zone, which is 1.5 times E office, which is office employment in zone I. E other is other type of employment in zone I, and retail employment in I zone. Zone I is E RET, E retail, and you have certain coefficient associated with that. And HI is the number of household in a zone I. And then you have two zones in the analysis. These are your zone 1 and zone 2. And for each of those zones, you're given these characteristics. So these are what we call your X values. Okay, so your X values. So these are what we call our X values, or the values, i.e. the values of the independent variables. Right? X values are the values of independent variables. And your job is to apply this regression model and figure out how many trips are originating in and destined for each zone. And TI defines the number of trips originating in zone I. And TJ is percent trips destined for zone J. Okay? So if I say TI, that's the formula. So I'll need to figure out how many answers am I looking for. I'm looking for T1 and T2. Okay? So that's your TI. Right? So these are, I'm looking for T1 trips originating in each zone. But then I'm also looking for two more values. I'm also looking for T1 and T2 based on the TJ equation. So I'm looking for T1 and T2 not just based on this first equation, but I'm also looking for it based on this equation as well. Okay, so let's see, let's get on with it. If I'm trying to figure out household values, I can figure out, so I can figure out T1 originating. So I can figure out T1 and then I can do the same thing for T2 originating trips as well. If trips start at a location, we call it the production. Okay, so this production, if trips originate in a certain zone, they start in a certain zone, we call it a production of trips. And if trips end in a certain zone, we call the attraction of that zone. So let's look at T1 originating trips and T2 originating trips. For originating trips, this is the formula we use. For originating trips, this is the formula. And it's pretty simple to apply this formula using this number. So I'll just plug in 10,000. So T1 originating trips for me would be equal to 1.5 times 10,000. So that will be equal to 15,000. And I can do the T2 originating trips. That's pretty simple too. I will just do 1.5 times 15,000. And why 15,000? Because where do you get 15,000? Because zone 2 has number of household equal to 15,000. Okay. Now, if I'm trying to figure out the destination trips are a little bit trickier because they have a different equation and they rely on 3 different independent variables. So they have a different equation, this one right here, and they rely on E office, E other, and E retail. But that's pretty simple too, because I could figure out trips originating. So I could figure out T1 destination, T1 destination trips. So how many trips will be destination in zone 1? It will be 1.5 times E office, which is 8,000, plus 1 time 3,000, because that's E other, plus 0.5 times E retail, which is 2,000. And I can quickly do the arithmetic on this. And that will be 12,000, 15,000, and 1,000, about 16,000 trips. Okay, so that's good. Now, what I want you to do is I want to figure out T2 destination and see if you can get the answer to be the correct answer here. I just did the calculation and I got the answer to be 20,750 trips. And I want you to be able to verify this answer by applying the characteristics of zone 2. So remember, this column represents the characteristics of zone 2, and apply those numbers to this equation. Now, it looks like T1, the zone 1, has 15,000 trips that then go to zone 2, and assume that there are no intrazonal trips, right? Assume that there are no intrazonal trips. So what I have here is that I have 15,000 trips starting at zone 1. Okay. And 20,750 trips is what zone 2 is attracting. Okay. The same idea. Zone 2 is producing 22,500 trips. Okay. Zone 2 is producing 22,000 trips. But T1 is only attracting 16,000 trips. Okay. Assuming you can ignore the intrazonal trips, that is what's going on. Okay. Now, that's not right. Like if it's a self-containing area where there are only 2 zones, and let's assume for a second, like if you do a regional analysis, typically that's what we assume is that number of productions from a zone have to equal to the total destinations for that zone. And now, because we only have 2 zones here, and that's the kind of level of problem that we're going to deal with in this chapter and this class, what should I do? Because one of these numbers is off, right? Because T1 is leaving out 15,000 trips are leaving zone trips are leaving zone 1, but T2 is destination for 20,750 trips. That's not possible, because it should only be home to 15,000 trips. If it's a self-contained area and you have number of trips going from zone 1, they're all ending up in zone 2. Now, here we make an assumption typically is that the numbers for home ends are considered more accurate. So we always consider the number of home ends to be more accurate. So which equation do you think we are going to think of that more accurate? This equation will be more accurate because this is based on the household characteristics. Okay, so number for the home end trips are considered more accurate. So now, so that means I only have 22,500 trips and 15,000 trips. So I'll have 37,500 total trips that I need to be distributing between my 2 destinations, because I'm going to assume this trip to be more accurate. So which one am I going to adjust? This is morning peak hour. So I'm going to adjust the destination trips, because my origination will be at home-based model. The origination model is a home-based model. So I'm going to assume that to be more accurate. And because I'm talking about AM peak hour, the trips start at the morning level. Because if this model for a PM peak hour, the destination model will be based on the household characteristics. And then I'll consider that to be a more accurate model. So look into this. So anytime I have a discrepancy, I assume one of these to be more accurate. And based on that, I conduct my analysis. The number of trips produced at home from home to work must equal to the number of trips attracted at work. Two distinct models may give two results. So assume one model or the other to be correct and adjust the second. Okay. It is necessary to ensure that the total number of trip origins equal to the total number of trip destinations, because each trip must have two trip ends. So that's why we want to have those numbers. And then, as I said, typically numbers developed for the home end are consumed to be more accurate. And for morning peak hour, those will be the originating trips model. So we're going to consider this is the more accurate model. So then we can adjust our origins or adjust destinations. So in this case, we are going to adjust the destination model. So TJ prime, so T1 prime and T2 prime. So remember, we estimated the number T1 and T2 before. So T1 and T2 are the two numbers we're going to estimate, and they will be sort of, this is the formula we are going to use to make those corrections. And this is for over the two zones. We'll estimate our TI numbers, T1 plus T2, and then this is T1 destination plus T2 destination, and then this is the individual TJ, and based on that, we'll adjust the TJ prime. So we will adjust the numbers that are coming out of this model for the two equations, and you should be able to do that. And if you have any questions about that, feel free to reach out to me. And if you want to check your work in terms of adjusting your origins or destination, in this case, you'll adjust the destinations. If you're going to have any issues with that, please let me know. Okay. I want to stop here, and then we're going to start with the part 2 in the next video.